Say we look at our hypothesis test using the t-distribution. Okay, so example number 5. A random sample of 30 cereal servings has a mean sodium content of 226.9 milligrams with a standard deviation of 10 milligrams. Can the cereal maker conclude that the mean sodium content per serving is less than 230 milligrams at a 0.01 level of significance? Okay, so it looks like there's a lot going on in that question, okay, as you read through it. Okay, but as you go through this content, what you want to think about is what kind of question is it? Well, is it telling you to construct a confidence interval? Well, no, it doesn't say construct a 90% confidence interval or 99% confidence interval. Okay, so what we're looking at is, can the cereal maker conclude that the mean sodium content per serving is less than 230 milligrams? So can they conclude something? Okay, means that they are claiming something. Okay, which means hypothesis test. So remember the 3 stages of hypothesis test. Okay, the way that I show you. You have to state your hypotheses. You calculate your test statistic. Okay, and then you make a decision. Okay, so when you form your hypotheses, okay, as you read this, can they conclude the mean sodium content per serving? Well, the mean sodium content means we're looking at mu less than 230 milligrams. So with your null and alternative hypotheses, when you set those up, mu less than 230 milligrams would be mu is less than 230. Well, remember, the less than or greater than or not equal to, those all go in your alternative hypotheses. So that is your alternative hypotheses, that mu is less than 230, and that is what we're claiming. Okay, that is our claim. So the null hypothesis, HO, will be that mu equals 230. Oops, sorry about that. Mu equals 230. Okay, so once we have our hypotheses written out, okay, now we have to collect the evidence and calculate a test statistic based on that evidence. So we collect our sample. Well, a random sample of 30 servings. Okay, so that tells you we took 30 servings, and that sample had a mean of 226.9. So that's your X bar, and that sample also had a standard deviation of 10 milligrams. So that's telling you that S equals 10. Okay, that sample resulted in 10 milligrams for the standard deviation. Okay, so now we're looking at our test statistic. Instead of saying Z equals, now it's a T, because we know the sample standard deviation, not the population standard deviation. So T equals X bar minus mu divided by S over the square root of N. Okay, that is our test statistic for T. Okay, so T equals the X bar, our sample mean was 226.9 minus our hypothesized mean, our expected mean of 230. Okay, we're assuming that 230 was true. And then divided by S, which is 10, over the square root of N, which is square root of 30. Okay, when you do those calculations, you get T equals negative 1.70. Okay, so that is our test statistic, negative 1.70. Okay, so now we need to make our decision. Okay, so what we're basically saying is, if the mean of the population was really 230, is a test statistic of negative 1.70, or a sample mean of 226.9, an unusual value? Is it unexpected? Is it too extreme? So remember, that is where you look at your curve. Okay, now we're looking at a t distribution rather than a z. And our test statistic of negative 1.70, okay, remember that 0 is right in the center, so negative 1.70 is going to be over here somewhere. And we're looking at the mean being less than 230. Well, our x bar value is 226.9. Okay, which means that we're at 226.9 will be this on an x-axis, or I'm sorry, on an x bar axis. Okay, so the idea is, or what we're trying to figure out is that too far away from the center if the mean really was 230? Okay, so it's 226.9, too far below 230 to consider that an unusual or extreme value. Okay, so mu being less than 230, that less than means we're looking out to the left here. So essentially trying to find what's the probability that t is less than negative 1.70. We have a little bit of a problem with that because our t distribution, when we go to the table, we did confidence levels before, confidence intervals. Well, now we're looking at is whether we have a one-sided p-value or a two-sided p. Okay, so when you look at the bottom of the table there, okay, we're shading to the left because the less than 230, we're shading to the left. So we're only shading one side of the curve. So we had a 0.01 level of significance. Okay, so in the question, okay, they told us a 0.01 level of significance. They're telling us that's what alpha is. Okay, so that's your alpha is 0.01. Okay, so what we're looking at here is 0.01 in one-sided p. Okay, so one-sided p-value. Now our sample size was 30, so we have to go to 29 degrees of freedom. Can we do that? Notice we get 2.462. Okay, so 2.462 on the left-hand side is going to be a negative 2.462. Okay, so that has to do with our alpha value of 0.01, which is basically saying that with 29 degrees of freedom, the area to the left of a t-value of negative 2.462 is an area of 0.01. Okay, so what happened with our sample is we only got to negative 1.70, which was not far enough away from that center of 0, from the center t-square of 0. Negative 1.70 is not far enough away from that to say that the assumption that mu equals 230 was no good. Okay, so just like with other hypothesis tests, we're at that same decision time where negative 1.70 is not extreme enough compared to negative 2.462 to reject HO. So our decision is we fail to reject HO, the null hypothesis. Okay, if that t-value was to the left of negative 2.462, like negative 2.5 or negative 2.6, then we would reject HO because that value would be more extreme than what we were willing to accept. Okay, so we failed to reject HO, which means not enough evidence to support the claim that mu is greater than, is less than, that mu is less than 230. Okay, so even though the 226.9 is clearly less than 230, okay, we're saying that that sample mean of 226.9, okay, which would be right here, is not extreme enough to reject that the mean could have been 230, okay, for all serial boxes. Okay, if we go on to the next one, okay, number 6. researchers collect a simple random sample of the times that 81 college students were required to earn their bachelor's degrees. The sample has a mean of 4.8 years and a standard deviation of 2.2 years. Okay, so when we read through this, the sample had a mean of 4.8 and a standard deviation of 2.2. So X bar is 4.8 and S is 2.2. So we're going to use a 0.05 significance level to test the claim that the mean time for all college students is greater than 4.5 years. So test the claim, that means hypothesis test. The mean time for all college students, so the mean time for all students is mu greater than 4.5. Okay. So I have this worked out, so just for the sake of time, again, we go through the three stages. We have our hypotheses, our test statistic, and our decision. Okay, so our hypotheses are pretty easy to set up in this one. Mu is greater than 4.5. That's what they're claiming in the question. So that's your alternative hypotheses. Your null hypotheses will be that mu equals 4.5. Your test statistic. Okay, so now we're going to collect the evidence. We're using the t-distribution because we do not know sigma. Okay, we're given S. The sample standard deviation is 2.2. So for your test statistic, X bar was 4.8. That's your sample mean minus the hypothesized mean of 4.5. That's what we think is true, that the population mean is 4.5. And then divided by S over the square root of n. Okay, so you get a t-value of 1.23. Okay, so our t-value for our test statistic is 1.23. Now we need to make our decision. So is that value of 1.23 too extreme or far enough away from the center to say that 4.5 was a bad assumption or a faulty assumption to make to begin with, okay, for the population mean? So we have our test statistic of 1.23. We're shading to the right because of the greater than. So we want to know, are we too far to the right or not? Okay, so greater than, we're shading right. The t-score for, or the t-value in the distribution, if you have alpha is 0.05. Okay, so it says use a 0.05 significance level. So there, alpha is 0.05, and we're in one tail again. Okay, so 0.05 and one tail, and we have a sample of 81 college students, so that means 80 degrees of freedom. So the 81 students tells us 80 degrees of freedom. There's 0.05 in one tail, so that gives us 1.664 for our cutoff value here. Okay, so again, 0.05 in one side of P because we shaded to the right. We just shaded one side, not both. Okay, so we shaded to the right. So one side of P is 0.05. 80 degrees of freedom gives us 1.664. Okay, so that is the value on our t-distribution that has 5% or 0.05 area to its right with 80 degrees of freedom. Okay, so we can see again that 1.23 is not far enough to the right or far enough away from the center to reject HO. So that looks like that mu equals 4.5 was an okay assumption to make. Okay, we cannot reject that idea. So our decision is we fail to reject HO, meaning when we examine the claim, if we do not reject HO, then we cannot support the claim. Notice I'm not saying we don't reject the claim. We're just saying that we don't have enough evidence to support the claim. Okay, so when you fail to reject HO, you're not rejecting the claim in this case, you're just failing to support it. Okay, in part B, using a 0.05 significance level to test the claim that the mean time for all college students is different from 4.5. Well, what changes in this one, being different from 4.5, means we're looking at our hypotheses as being not equal to 4.5. Okay? And that is our claim. Okay, so different from meaning not equal to. Okay, much of the steps will be the same. Your test statistic is going to be the same number because the values didn't change at all in your test statistic. Okay, but now when we make our decision, just like with the other hypothesis test, the not equals to means that we're shading on both sides of the distribution. Okay, so when we look at both sides of the distribution, what we're looking at now is area to the right and to the left. So now what we're looking at is we're looking at a two-sided P. Okay, so now in our T distribution, a two-sided P has 5% because alpha is 0.05. Notice it has 0.025 in one side, which means there's 0.025 in each side, or 0.05% for the total of the two sides. Okay, so 0.05 in those two sides with, let's see, we had 80 degrees of freedom again. So 80 degrees of freedom gives us 1.990 for this one. Okay, so now the T value are positive 1.990 and negative 1.990. And each of those has 0.025 area to their left. Okay, for a total of 0.05 area. So what does that tell us to do? Well, again, we're going to fail to reject HO because that 1.23 is not extreme enough. It's not past the 1.990 on the right-hand side or to the left of negative 1.990. It's in neither one of those areas. So 1.23, that t-score is not extreme enough, which means that sample mean of 4.8 was not far enough away from 4.5 to say that 4.5 was a bad assumption. So we failed to reject HO, meaning not enough evidence to support the claim that mu does not equal 4.5 years. Okay, next example. Okay, law enforcement agency claims the mean speed of cars traveling on a certain stretch of highway is greater than the posted 65 miles per hour speed limit. Okay, so they're claiming that the mean speed is great for all cars is greater than 65. So the mean speed greater than 65. So they're claiming mu is greater than 65. So that's going to go along with your hypotheses. Okay, and then if we look at them taking a simple random sample of 35 recorded speeds, so that's your value of n, that's your sample size, resulted in a mean of 67.4, so there's x bar, and then a standard deviation of 5.7, so that's s. And again, s because that resulted from your simple random sample. So can the agency's claim be supported at a 0.02 significance level? So again, that is your alpha value. Okay, so just like every other hypothesis test, remember we state our hypotheses, calculate our test statistic, and then make a decision. Okay, so on this one, our hypotheses, well, they were claiming that the mean speed was greater than 65. So when we set that up, okay, we have mu equals 65 will be our assumption for the null hypothesis, and mu greater than 65 will be the alternative hypothesis, okay, which is also our claim. Okay, calculate our test statistic. Well, because we have our sample standard deviation, we're going to use the t distribution. So x bar minus mu divided by s over square root of n. Substitute in our values. The sample mean 67.4 minus hypothesized mean of 65 divided by s over the square root of n. Okay, so 5.7 over square root of 35. And our t value is 2.49. Okay, so our t-score 2.49. Now we have to make our decision. based on a 0.02 significance level. Okay, so basically asking, is that 2.49 too extreme to say that the mean of 65 was a good assumption? Okay, or is the sample mean of 67.4 too extreme to say that the 65 population mean is a bad assumption or faulty assumption? Okay, so we draw our curve, and our test statistic of 2.49, okay, we put that on our axes, greater than 65, we're shading to the right. So what we're looking at is that 2.49 too extreme? We have to compare that to what t-score has 0.02 to its area to its right if you have 34 degrees of freedom, because we have 35 sample values, or 35 values, so we have to find 34 degrees of freedom. Okay, so when you look that up in our table, 0.02 in one tail, okay, so a one-sided p, 0.02, okay, is right here. And 34, notice that's not in our table. We skip from 30 to 40. Okay, so it's either 2.147 or 2.123. Okay, so what I used was the 2.147 because that'll allow you to be more cautious in your rejection region. Okay. Okay, so when you compare the 2.49 to 2.147, okay, then that 2.49 is farther to the right. So our decision about HO will be to reject HO. Okay, well, that's what that tells us about our claim now. We reject HO, so we're saying that mu equals 65 was a bad assumption, okay, or faulty assumption. So it does look like mu is greater than 65, has enough evidence to support that. Okay, so there's enough evidence to support the claim that mu is greater than 65. Okay, at part B, at what significance level would the claim not be supported? Okay, so what we're looking at here is that we see that 2.49 is greater than 2.147. So at what point would you not support the claim? Okay, so if we're looking at the 2.147 is right here. Our test statistic of 2.49, okay, so 2.49, you want to see with 34 degrees of freedom, but again, we're looking at 30. Okay, just because that's the value that we're rounding down to here.